Okay, welcome to Let's Get to the Marks. We're going through GCSE Chemistry Paper 1 for higher paper. You got an hour and 45 minutes, and this is the 2021 paper. I'll put the links in the description. If I don't remember, remind me in the comments. Okay, so let's look at question one. Question one. This question is about carbon and its compounds. Fullerenes are molecules of carbon atoms. The first fullerene to be discovered was Buckminster fullerene with a molecular formula of C60. What shape is the Buckminster fullerene molecule? Well, hopefully you all know this. It's shaped like a football. So the word for that is a sphere. Don't say circle because circles are two-dimensional. So it's like with the plum pudding model. You mustn't say circle. We call it a sphere, or you can probably get away with the word ball. Now, the next part to the question is give one use of a fullerene. So what are these balls of 60 carbon atoms used for? And the answer is nano cages for delivery of drugs. Also, they can be used as lubricants. Okay, they got weak intermolecular forces between the molecules, and so they slide and can be used as lubricants. There are plenty of other uses for them, but these are the main ones you should know about. All right, moving on. So here we have propanone is a compound of carbon, hydrogen, and oxygen. Figure 1 shows the dot and cross diagram for a propanone molecule. Here's figure 1. You can see here we've got the electrons shown by crosses and circles. Obviously, each bond is made up of a pair of electrons, and occasionally you'll get a bond with two pairs of electrons. That is a double bond. Let's look at the question. Right, it says complete figure 2 to show a propanone molecule. Use a line to represent each single bond. Use figure 1. So you've got to complete figure 2. And if we zing back up to figure 1, we check it out, you can see that each of these hydrogen atoms is connected to a carbon by a pair of electrons, and you need two electrons to make one black single line, a single bond. Okay, so we can see we've got a single bond here to a carbon, a single bond here to a carbon, and then single bonds to each of these hydrogens. So let's go and add that on to the diagram below. And you might notice here we've got the 4 electrons. That's the double bond from the C to the O that you'll see on the diagram below. So what we need to do here is add a carbon and then 3 hydrogens. Each black line represents 2 electrons that are shared. Call these a covalent bond. Okay, neat. Right, the next part to the question, determine the molecular formula of propanone. So you've got to give the molecular formula. The molecular formula is how the number of atoms of each element within the molecule. So we want the number of atoms of each element. So I'm going to count out the carbons. We've got 1, 2, 3. So first thing we can do is write down C3. And then for the H's, we have 1, 2, 3, 4, 5, 6. So it's C3, H6. And then how many O's do we have? We have 1 O. C3, H6, O. And that is the molecular formula. Now, you might be asking yourself, can I put H6? What if I count the H's first and then C3, then O? There's an order to this when we're writing what we call organic molecules, things like propane, propanone, propanol. What you have to do with those is you start with the carbon, then the hydrogen, and then whatever else is added on, like the oxygen. So you always start with carbon, then hydrogen in hydrocarbons. You don't start, even though this isn't a hydrocarbon, it's an organic molecule, but you don't start with a hydrogen. Okay, another little quick check. When you're drawing these out, carbon is a group 4 element. Always make sure there is 4 bonds only around each carbon atom. See this carbon here? It's got 1 to the side there, 1 to the side there, and then 2 to the oxygen. So that's a total of 4 bonds. Carbon can have a maximum of 4 bonds. All right, let's move on. So we get 1 mark for that and 1 mark for that. Now, 1.5, propanone is a liquid with a low boiling point. Why does propanone have a low boiling point? So in chemistry, you need to know this off by heart. Anytime something has a low boiling point or low melting point, it means that it has weak intermolecular forces. This one here, okay? All bonds are strong. There is no such thing as weak covalent bonds. And intermolecular forces are weak, although you can have some intermolecular forces that are stronger than others. So if you had two molecules that have intermolecular forces, they're all weak, but one can have slightly stronger than another and therefore a slightly higher boiling point or melting point. But anytime you see the word low boiling point, low melting point, you need to be thinking simple molecule with weak intermolecular forces. If you can't remember the word intermolecular forces, you can say weak forces between molecules, which means the same thing. Okay, let's zing on. Okay, we've got 1.6, it's a 6 marker. So 1.6, figure 3 represents the structure of graphite. Here's figure 3. So we've got the structure of graphite here. Explain why graphite is a good electrical conductor and why it's soft and slippery. You should answer in terms of structure and bonding. So when they tell you to talk about structure and bonding, you need to name the structure. And there's only two structures available in chemistry. And then there's three types of bonds. So we want to name the structure. You've got a 1 and 2 here, and then the type of bonding. And there's three types of bonding. So you need to know those off by heart. And then we need to explain why it's a good at conducting electricity and it's soft and slippery. So I suggest you pause the video and then have a go at this one and then watch me go through the answers. Okay, let's go through it. So first off, what type of structure have we got? Well, the structure can either be giant or simple. When you look at that, many atoms connected by lots and lots of bonds. This is a giant structure. And the bonding is covalent with lots of strong, all bonds are strong. So anytime you talk about bonds, just call them strong, with lots of strong covalent bonds. All chemical bonds are strong. Some are stronger than others, but there we go. So I've just said there's a giant structure with lots of strong covalent bonds, and that's basically explained that bit of structure and bonding. Now I want to talk about why it's a good electrical conductor. I could add a bit more about the structure just for the sake of it. If you look at graphite, graphite has, if you look at each atom, it's connected to three other atoms. So each carbon atom is bonded to three other atoms. You might say, hey, what about this one here? This is only bonded to two. Yeah, but this would go on again. This sheet would carry on and on and on, kind of to infinity, as in there'll be trillions of atoms in one of these sheets. Okay, so we can say each C atom, that means carbon atom, in graphite is bonded to three others. As carbon is in, do you remember what group I said it's in? It's in group 4. This means it has one electron not bonded. So what I mean by that is each one of these black spheres that you see here, or these black dots, is a carbon atom, and they have three of their electrons in their outer shell. Now they're group 4, they've got 4 outer shell electrons, but 3 are in bonds. One is left on its own to roam. Do you remember what we call that? We call those delocalized electrons. So that's where the delocalized electron comes from, the fact that only 3 of its outer shell electrons are bonded. So we say it has delocalized electrons that can carry charge through the structure. Now, depending on the exam board you do, they'll allow you to say carry current through the structure, but technically you should say charge. Current is actually the rate of flow of charge. The key words here, when you're talking about why something conducts electricity, if it's metals or graphite, the answer is it has delocalized electrons that carry charge through the structure. So that's covered that bit. The last bit of this 6 marker is why is it soft and slippery? So if we're talking about why it's soft and slippery, we would say graphite is arranged in layers, which you can see there. We've got 3 layers of graphite. Obviously, if you looked at your pencil that you draw in art or in school with, that is made up of many millions of layers of graphite, and each layer contains millions and millions of atoms bonded by strong covalent bonds to each other, which explains why it has a high melting point, but they haven't asked us that here. So graphite is arranged in layers with weak intermolecular forces between the layers. Now, to be honest with you, this is the confusing bit. Normally, weak intermolecular forces are only found in simple molecules and they're not found in giant molecules. But the fact that there are weak intermolecular forces because there's no bonds between the layers. If this was diamond, which is also made of carbon, there'd be solid covalent bonds between the layers. So you wouldn't have any layers. It'd just be strong covalent bonds everywhere. But instead, we've got weak intermolecular forces. I've shown these with the dotted lines. They're between the layers. They're easy to break. So the layers slide. And that's why it's slippery and soft, and graphite can be used as a lubricant as well. So this will get you all the rest of the marks. And in fact, there's probably about 8 marks there. So you can get, yeah, you'll definitely have all 6 for that. All right, let's move on. That's the end of question 1. How did you do out of 11? So I suggest that you pause the video and have a go before watching me go through the answers. So you might want to pause now and have a go at question 2 or the start of question 2. This question is about the atomic structure and periodic table. Gallium, symbol Ga, is an element that has 2 isotopes. Give the meaning of isotopes. You should answer in terms of subatomic particles. Now, there's kind of a bit of fluff to this question, so we want to say, give the meaning of isotopes. You don't need to say isotopes are, but it's just my sentence starter. So isotopes are atoms of the same element. So you can have 2 isotopes of gallium or 3 of carbon, whatever. Atoms of the same element that have the same number, whoopsie, number of protons, but a different number of neutrons. Okay, so the key bit there that everybody memorizes off by heart, and hopefully you guys have memorized it. Got a key bit here, and that is we want to say same protons. Think about it. The proton number is the bottom number on the periodic table on an element. That is the atomic number. Why do we give the elements an atomic number that's based on protons? Because protons are the most stable particle in the whole of the universe. So they don't break down or change. Protons are the most stable particle, the least likely to change. So it'd be pointless naming an atom after its neutrons or numbering it after its neutrons, because you get different atoms with different amounts of neutrons, and those neutrons can change due to radiation, which you study in physics. So we number atoms by their proton number. So protons stay the same, but the number of neutrons are different between isotopes. So I like to start off by saying isotopes are the same element. Some people like to answer this in terms of an element that has the same atomic number but a different mass number. Some exam boards will allow that, but not all exam boards. So there we go. Beautiful. Let's move on. Okay, we're on 2.2 and we've got a little calculation to do here. This shows the mass numbers and percentage abundances of isotopes of gallium. So we've got the mass number 69, percentage abundance 60, and 71 and 40. Calculate the relative atomic mass, AR, of gallium. Give your answer to 1 dp, and it's 2 marks. So you've got to remember that. I personally think using a highlighter is key, because if you don't use a highlighter, you could do all the hard work and then miss out on that easy 2nd mark. Okay, so what do you want to do here? Well, there's an equation for this, and it's basically the sum of the mass number times the abundance of each element. So 69 times 60 and 71 times 40. Add that together to make the sum of it, and then divide by 100. So let's whack that in. So in your calculator, you'd use brackets, hopefully. 69 times 60, you bracket that, and then you're going to add that because we want the sum of the mass number times the abundance for each element. And we whack that in our calculator, and then we divide that by 100. You divide it by the total abundance. Now at A level, that can be a different number than 100, but at GCSE, the total abundance always equals 100. So that should be dead easy. Let's smash that in the calculator now and see what that comes to. So let's go 71 times 40. That equals 6,980. We divide that by 100. So our answer should be 69.8, and that is 1 decimal place, 69.8. Hopefully that's right, and I haven't screwed that up. All right, let's go. Okay, 2.3 is the next part of the question. Give numbers of electrons and protons in an atom of the isotope GA, and just in case you can't see on the screen, 69 and 31. So the number of electrons, well, the atomic number down here is the number of protons, and you should know that protons is equal to electrons in a neutral atom. And they've used the word atom, not ion here. So we know that protons and electrons are the same. So that should be 31. And then we have the mass number, which is protons plus neutrons, because they're the only things in the atom that have mass. Electrons' mass is negligible. It's like tiny, isn't it? 1 over whatever it is, 1,000 and something. Right, so P plus N. So we want to do P plus N minus P. So 69 minus 31, and we're going to get 38. And there you go. Bim bam bomb. Right, next thing says, what is the most likely formula of a gallium ion? Well, we'd have to know what blooming group gallium is in. So we'd have to look up on our periodic table and see what group it's in. But it may give us a clue in the stem of the question. And it does. Check this out here, guys. So you don't even have to bust out the periodic table. AQA are nice like that. That is the worst color to highlight in. But essentially it tells us that gallium is in group 3. So what do you reckon? What is the most likely formula of a gallium ion? Well, if it's in group 3, it has 3 electrons on the outer shell. Okay, so is it going to take 5 to get 8, or is it going to give away 3? Well, all metals give away electrons and become positive ions. So gallium, it's in group 3, it's going to throw those 3 away and it's going to become Ga3 plus. Why is it positive and not 3 minus? That's because electrons are negative themselves. So if you give away electrons, you lose negativity and you become more positive, because you still maintain your 31 protons in the nucleus, but now you've only got 28 electrons. So you've got an overall plus 3 charge. 30 minus 31, minus 28 plus 31 in the nucleus makes plus 3 overall. All right, let's zing on. We're nearly at the end of question 2. So gallium was discovered 6 years after Mendeleev published his periodic table. Give 2 reasons why the discovery of gallium helped Mendeleev's periodic table to become accepted. So he left gaps that predicted where new Sugar Ray Leonard elements would be found. So he predicted gaps for like things like gallium, and more evidence to support his theory. Why? Well, as when gallium was discovered, its properties fit the group with the gap in. So when he discovered gallium, its properties, whether it was silver, shiny, could conduct electricity, was reactive with water, whatever those properties were, they fit the group that gallium slotted into. So it was like, all the evidence came together to support his theory. And there's the 2 marks. Okay, let's zing on. Okay, we're on question 3 now. This question is about the extraction of metals. Element R is extracted from its oxide by reduction with hydrogen. The equation for the reaction is 3H2 plus RO3 goes to R plus 3H2O. Now, R is not actually the symbol for any element in the periodic table. This is just like an algebraic symbol, and you're going to have to work out probably what R is, but I don't know that yet. 3.1, the sum of the relative formula masses, the MR of the reactants, 3H2 plus RO3 is 150. Calculate the relative atomic mass of R on its own. Well, they've just told us that the reactants equals 150. Calculate R. Well, we know oxygen is 16, so we want to do 150. Up on blind. Molybdendium. There we go. 96. MO, and that is molybdendium. Okay, and I'll get us a mark. Lovely. Okay, let's move on. Sugar over ticking. Okay, looking at 3.3, carbon is used to extract tin from tin oxide. The equation for the reaction is tin oxide plus carbon goes to tin plus carbon dioxide. Calculate the percentage atom economy for extracting tin in this reaction. So the key thing with atom economy is you're looking at the AR of the useful products over the AR of all the products. Different ways to do it, but that's the way I'm going to do it. So looking, I don't know why I got grey going on an old highlight. Oh, it's a stupid color, isn't it? So tin, it tells us right here, we're extracting tin. So that's our useful product. So how much is tin out of both of these? So what we want to do is, and it's a percentage because it wants percentage atom economy. So we want to do 119, which is the tin, and we want to divide that by the total, which is 119 plus carbon dioxide. Now, carbon dioxide is 12 plus 2 times 16, which is 32. So we're going to do 119 over 44 plus 119. So it's going to be quite a high atom economy. And it's 163. So we want to do 119 divided by that, bish bash bosh, times 100. We're going to get 73. So times 100, and we're going to get 73% atom economy. Superbulous. Lovely. One thing I would say that isn't shown here, but sometimes when you're working out AR, you do not normally include the balancing numbers. But let's say that was 2 and that was 3, my coefficients. With atom economy, you are doing the atomic mass of useful products over the total atomic mass, but you have to include the coefficients. So in this situation, you would double 119 and you would triple the carbon dioxide when you add up the total. Okay, so it's really the mass of the useful products over the total mass of the products, all of the products. Anyway, if that was as clear as mud, I wouldn't be surprised. Here we go. 3.4. Tungsten W is a metal. Tungsten is extracted from tungsten oxide, WO3. All other products from the extraction method must be separated from the tungsten. Table 2 shows the information about 3 possible methods to extract tungsten from tungsten oxide. So we've got method 1, reactant, carbon, cost low. Products, tungsten solid, carbon dioxide, tungsten carbide solid. 2, hydrogen, cost high, tungsten solid and water vapor. Method 3, we're going to need iron as a reactant. The relative cost of the reactant is low. Products, you get tungsten solid and iron oxide solid. Okay, so they want us in this question to they want us to evaluate 3 possible methods for extracting tungsten from tungsten oxide. What I suggest when you get evaluate is you say something good and bad about each of the 3 methods. Something good, something bad. Don't use the word good or bad, but something positive, something negative about each of those, and then make a final choice of which method you think is best and back it up with something from the table. So nice and simple. If we look at carbon, we'd say um, the cost of the reactant in method 1 is low compared to method 2. So there's a little comparison, right? What I would also say is, um, however, method 1 produces CO2. What do we know about CO2? It is a greenhouse gas. So that's my good and bad. It's cheap, but it makes a greenhouse gas. Um, it's also going to have a low atom economy. Look how many products are made there. I would predict that method 1 has a low atom economy, which isn't so good. All right, method 2. Um, method 2 cost is high. However, it only produces water vapor as a side product. So easy to separate or purify, right? Like very easy to purify at the end because you've not got two solids. With tungsten solid and tungsten carbide solid, what you should say for method one as well, which I haven't said, is that it's going to be harder to separate those two solids, potentially. And then method three is also a low cost, so that is good, right? Um, however, produces two solids in the product, so may be difficult to separate, but does not produce any greenhouse gases. And I'm going to end with, so I believe method three is the best. So I'm giving you my opinion that method three is the best based on the fact that it's cheap and no greenhouse gases. So there you go. That's my evaluation. And you're going to pick up 4 juicy marks. Okay. Lovely jubbly. Awesomeness. Let's move on. Right. We're up to question 4. This question is about group 1 elements. Give 2 observations you could make when a small piece of potassium is added to water. So this is a really common question. You should know these off by heart for sodium, lithium, and potassium. All of these alkali metals will float in water. So we could say they float on the water. Okay. They move about on the water. All of these alkali metals produce hydrogen, so we can say they effervesce or they produce bubbles. Because you're dealing with water, a liquid, whenever you get a gas and a liquid or a solution, you're going to see bubbles. You can't say you're going to see bubbles if it's just a gas produced from a solid, but if there's a liquid or a solution about, you're going to see bubbles. So we can say bubbles, floats on water, moves about on the water. With potassium specifically, you have to know, you would see a lilac or a violet, we could say, or purple flame. And this is because the heat that's produced in this very exothermic reaction causes the hydrogen bubbles, the bubbles of hydrogen gas, to catch a light, and they burn with a violet flame in this situation. If it was sodium, you get a more of a yellow flame. Okay. Fizzing, whizzing, sound, whatever. It moves about pretty fast, this one. Anyway, any of these two would give us the marks. Okay, let's move on. Okay, we've got a little balancing equation to do here. So pause the video, have a go. You should balance this equation for 2 marks. KH2O, this one you need to know off by heart. It's a very, very common question. It's something that they love to ask you. Okay, you don't need to put state symbols in here, but when you drop an alkali metal into water, you produce hydrogen. That's where we got the bubbles of gas from. And you produce an alkaline known as metal hydroxide. That's why they're called alkali metals, because they make an alkali. The metal itself is not an alkali. It's because alkali metals produce an alkaline solution. And by the way, they often ask you to put state symbols in, excuse me. They didn't ask here, so you won't get any marks for this. I'm just doing it for revision purposes. And they love this equation because check it out. It's one of the only equations where you get all 4 state symbols. So it's a great one to ask in exams. Okay, if we balance this, the way I balance this up, I'm going to say, right, I've got 2 H's there, I've got 1 there. I'm going to minimum need to put a 2 here. Why? Because I've got 3 H's otherwise. How are you going to get 3 H's? You've got a 2 here, so I need an even number. Now I've got 2 times H and H2, I've got 4 H's. So I can put 2 here. That's going to give me my 4 H's. Look, I've also got 2 O's there and 2 O's there, and now I've got 2 K's. So it's just 2, 2, 2. Boom. Okay. Explain why the reactivity of elements changes going down group 1. In fact, this pattern, just for your own chemical knowledge, boom, as you might want to know, is the same for group 1, group 2, and group 3 metals. It's the same for all metals, okay? But we study group 1 because the reactivity is more accentuated because they're very reactive. So as you go down from lithium, it's got 1 electron in the outer shell. If it was group 2, they'd have 2 electrons in the outer shell, but the pattern would be the same. So as we go down, Why is it that sodium is more reactive? And the answer is we need to break this down. Okay, so we say the atoms get bigger. Okay, you could use a more technical term. We could say they have more shells. That's better to say they have more electron shells. Okay, what does that mean if the atom's bigger or they have more electron shells? The outer electron is further from the positive nucleus. Now, nucleuses are always positive. You could just say further from the nucleus. Therefore, it is less attracted to the nucleus. Okay, so there's less attraction to the nucleus because the nucleus is positively charged and the electron's negative, and if that distance is greater than over here, there's less attraction. Okay, and then we want to say, so it is easier to remove or lose the electron. Okay, so that's definitely going to get you your 4 marks. Something that is sometimes on the mark scheme is that as we go down the group, we can say shielding increases, and that is a definite mark. It's more of an A-level term, an AS level term, something you do in the first year of A-level chemistry. Shielding just means as we go down the group, or you're going to be going down the periods. So as lithium's in period 2, it only has 2 electron shells. And this electron is shielded from the positive charge of the nucleus by that electron shell. Well, sodium has 3 electron shells, and that means this electron, the negative charge of that electron is less attracted to the nucleus because there's 2 layers of other electrons in between it that are shielding the feeling of attraction from the nucleus. So as you go down with each element, there is more shielding and the electrons are less attracted to the nucleus. All right, awesome. 4.4, sodium reacts with oxygen to produce the ionic compound sodium oxide. Oxygen is a group 6 element. Draw a dot and cross diagram to show what happens when atoms of sodium and oxygen react to produce sodium oxide. So we only really need to focus on the outer shell to show what's going on here, but we can show all the shells if we want. But we can show just the outer shell if we like as well. Oxygen is in group 6. So if I was to look up oxygen in my periodic table, I'd find out that it has 8 electrons. So it's got 2 in the first shell and it's got 6. And make sure you pair up your electrons. Boys tend to be really rubbish at pairing the electrons up. Just something I've noticed through years of teaching. Sodium is in group 1. Now, sodium, okay, again, I like to only show the outer shell. I can't be bothered with this stuff, but it's 281 for sodium. Oh my days. You can see why I can't be bothered. I got a D grade in GCSE art. So sodium has 11 electrons, and that means its formula is, or its electronic configuration is 281. I prefer just to show outer shells. So we can see what is actually going to go on here. Draw a dot and cross diagram to show what happens when atoms of sodium and oxygen react to produce sodium oxide. Well, look what's going to happen. This electron over here is going to go wandering over here. So that electron is going to go there, and that's going to leave that outer shell. It's going to disappear like that. Now, you can draw this sodium again, which I will, but in the exam, why do I need a second electron? Well, I need a second sodium atom because oxygen is unhappy with only 7 electrons. This sodium would be very happy, but the oxygen would be unhappy. So what I need to do is draw another one of these. Look, 1, 2, this is long, long, long. Oh gosh, I'm dying of death here. And that outer electron is going to jump over here too, and we're going to cross out that one to leave behind like that. Now, guess what? Instead of doing all of that painful business, what you can do, because you're supposed to put brackets around ions as well. So if we want 4 marks, we need to put brackets around them. And then we need to put the charge for the ions. So oxygen has gained 2 negative electrons, so has a -2 charge, and sodium has a +1 charge. Now it's really long. You can do this, and this will get you your 4 marks. 2 sodium ions, each with a plus charge, and 1 oxygen ion with a -2 charge, brackets around all of them, correct amount of electrons, full outer shells there and there. Boom, 4 marks. Guess what? You can also do this if this is all easy for you and you need to save yourself time in the exam, you can just put a 2 there to say there's 2 lots of sodium ions, or you can put a 2 here just to let the examiner know that you're aware there are 2 sodium atoms, and that will sort you out. Okay, 4.5. Why is oxygen described as being reduced in the reaction between sodium and oxygen? So, why is it described as being reduced? Um, well, if you take, I'm just going to show you the reaction here. So, if you take sodium and oxygen, you actually don't need to know this reaction like this. You do need to know this reaction off by heart, but obviously we just drew the ionic bonding for it. So it was Na2O. So I'm going to need to put a 2 in front there so that I have 2 oxygens to match that. And I'm going to need a 4 here. Anyway, forget that. Coefficients, that's just me showing you the balanced equation for it. So solid, gas, and solid. By the way, all group 1 metal oxides are solid and white. So anything from group 1, 2, or 3, any metal from group 1, 2, or 3, when it's joined to any non-metal, will be white in color and colorless when dissolved in water. All right, anyway, waffling on. What's going on here? Well, what's happened to the oxygen? Well, what's happened is the sodium has become plus, remember? And the oxygen has become minus. And hopefully you can remember the term oil rig. And that means oxidation is losing electrons. So we should be able to work out what lost the electrons. Well, the sodium was oxidized because it lost electrons. And you can see rig, reduction is gain. The oxygen was reduced. It gained electrons. It gained 2. Another way that some students prefer is old Leo grrr. Yeah, so that means loss of electrons is oxygen, or gain of electrons is reduction. Leo grrr. Okay, enough of that rubbish. Those are little reminders on how to remember to do that. Right, 4.6. Explain why sodium oxide has a high melting point. So why does sodium oxide have a high melting point? So first of all, you need to identify what it is. But what I would say is the moment I see the words high melting point, you're going to have to talk about the structure in chemistry. Now, anytime you have a high melting point, high boiling point, or you're dealing with a strong solid, it's going to have a giant structure. So I know if I know nothing else, I'm going to get 1 out of 3 marks from writing giant structure. Okay, so as soon as I can now get the bonding wrong if I want, but anytime you have a high melting point or boiling point, it's giant. It could be giant metallic, giant ionic, or giant covalent. If it's low melting point, it's a simple structure. If it's low boiling point, a simple structure. If it's a gas or a liquid, all gases and liquids at room temperature have a simple structure. So water, carbon dioxide, oxygen, hydrogen, methane, literally any gas you can think of at room temperature, or any liquid, has a simple structure. So alcohol, simple structure because it's a liquid at room temperature. Petrol, diesel, those are liquids at room temperature. They all have simple structures. Any solid at room temperature, you're likely to have a giant structure. There are some simple structure solids like iodine that are solid at room temperature, but the forces are so weak that they sublime. Anyway, let's move on. Right, so I know it's a giant structure. It's metal and non-metal. So guess what the bonding is? Metal and non-metal. Hopefully you know that off by heart. So it's going to be, it has a giant ionic structure. Now, I always like to put the definition of the type of bond down as well. So strong attraction. This is what an ionic bond is. It's strong attraction between oppositely charged ions. Now, yes, if you want to be technical, super duper, you call it a strong force of electrostatic attraction between oppositely charged ions. If it was covalent bonding, we'd say a strong force of attraction between shared pairs of electrons and positive nuclei. And if it was metallic bonding, we would say strong electrostatic attraction between delocalized electrons and positive metal ions. But it's not, it's ionic bonding. So we want to say it has a giant structure, It's got strong ionic bonds, or you could say strong attraction between oppositely charged ions. So what is that? That is a strong ionic bond. Now, sometimes in the mark scheme, they'll just give you the mark for saying it's got strong ionic bonds. Sometimes they want you to explain what the ionic bond is. So strong attractions between oppositely charged ions. And then all we need to say for the last mark is lots of energy needed to break or overcome the bonds. So essentially, your key points here, I'm going to circle keywords giant. Could be ionic bond, but you may have to say this whole spiggly biggly. It all depends on the mark scheme. That bit can be alternate. And then we just say lots of energy to break. And that will get you 3 marks. Awesome. Okay, we're going to move on. Oh, I didn't even answer this question. I talked about it, but I didn't even write the answer down for this question. So why is oxygen described as being reduced? You didn't even have to do all that working out. If you just remember oil rig, we just say it gained electrons, which I did explain, but I forgot to write down the actual answer. So there we go. Boom. Okay, let's move on. Question 5. Let's come alive. This question is about salts. 5.1. Name the salt produced by the neutralization of hydrochloric acid with potassium hydroxide. So what you have to do here is know your 3 different acids: hydrochloric acid, sulfuric acid, nitric acid, and the salts they make. So hydrochloric make chloride salts, nitric acid make nitrate salts, and sulfuric acid makes sulfate salts. Phosphoric acid makes phosphate salts. You get the idea. Okay. Now, the name of the salt, you take the metal from the alkali and you mix it with the name part of the acid. So it's going to look like this. Potassium hydroxide plus hydrochloric acid is going to make potassium chloride. You always get the first part of the salt's name from the alkali and the second part from the acid. So this comes from the acid, and the first part of any salt's name comes from the alkali, and it will be the metal that's in the alkali. So if it was sodium hydroxide, this would be sodium chloride. If it was magnesium hydroxide, this would be magnesium chloride. And if this was sulfuric acid, this would be potassium sulfate instead of potassium chloride. So you get the idea. Write an ionic equation for the neutralization of hydrochloric acid with potassium hydroxide. I just want to show you this one, but actually you can just memorize this. You can work it out, but you can memorize it. So let me show you what we're, yeah, right. There's potassium hydroxide. We're adding it to hydrochloric acid. Boom, boom, boom. We're going to make, what did we just say it makes? Potassium chloride. Oh my days, that K got stuck. And H2O. That's all balanced. We don't need to mess around with that. Now, technically, we have things in chemistry called spectator ions. These are things that either do not change their physical state. So we know potassium hydroxide is aqueous. We know all acids are aqueous. Potassium chloride going to be aqueous, and water's going to be liquid. Anything that changes its physical state can go into the ionic equation, or anything that changes its electric charge. Now, nothing changes its electric charge in this equation. Everything stays as +1, and the oxygen's -2, and the hydrogen's +1. So nothing, and the chlorines are -1. None of them change their ionic charge. However, they do change physical state. So does potassium change its state? It's aqueous here, and it's aqueous there. So what we say is potassium is a spectator ion. It does not change its physical state. It's aqueous on both sides of the equation. What about Cl, chlorine? It's aqueous here. What is it here? It's also aqueous. So the chlorine atoms or ions are also spectator ions. So what I'm left with is H, which is aqueous here, and OH, which is aqueous there, but they become L, liquid, over here. So they have changed their physical state. So we include them in the ionic equation, and I have to write them as ions. So it's going to be OH minus plus H plus, and this goes to H2O, and that is the ionic equation. And actually, you might be like, oh my gosh, I can't work that out. The ionic equation for neutralization is the same every single time. So you don't have to work out how to write ionic equations. Just memorize H plus and OH minus go to H2O. And if you were doing their state symbols, the ions are always aqueous. Okay, ions are always aqueous, otherwise they're not free to move. And then we've got our liquid for water because it doesn't have ions. Well, that's another story, but there we go. Okay, 5.3. Soluble salts can be produced by reacting dilute hydrochloric acid with insoluble solids. Copper, copper carbonate, and copper oxide are insoluble solids. So we've got copper, copper carbonate, and copper oxide. Which of these insoluble solids can be used to make a copper salt by reacting solid with dilute hydrochloric acid? So copper's very unreactive. Um, I mean, metal plus acid makes salt plus water. So you're going to make a copper salt if you use copper, copper carbonate, or copper oxide. They're all going to make a copper salt. It's a question of whether the exam board say copper is too unreactive. So in which case it would be copper carbonate and copper oxide only, because they may say that copper is too unreactive. But technically all three can react to make copper salts. If we were writing equations, copper can make copper salts because copper plus acid makes salt and hydrogen. Copper carbonate plus acid makes salt, water, and carbon dioxide. And copper oxide plus acid makes salt and water. But copper is too unreactive. So the answer is not this one. Nearly ticked the wrong one. It's going to be copper carbonate and copper oxide only. The element copper is right at the bottom of the reactivity series. If they'd said concentrated hydrochloric acid, you could make copper salts. So strong enough acid would form copper chloride. But if you're using dilute hydrochloric acid with copper, they're not going to react. All right, let's move on. Okay, a student makes crystals of magnesium sulfate. This is the method used. Add sulfuric acid to a beaker. Warm the sulfuric acid. Add a spatula of magnesium oxide to the beaker. Stir the mixture. Repeat steps 3 and 4 until the magnesium oxide is remaining in the beaker. So it's floating in the beaker basically. Filter the mixture, evaporate the filtrate gently until crystals start to form. Leave the solution to finish crystallizing. Give one reason for step 2, step 5, step 6. So step 2, warm the sulfuric acid. This is to increase the rate of reaction, increase the rate of reaction. By increasing the temperature, you increase the rate of reaction. So we want it to happen quickly. There we go. Yeah, let's move on. Step 5, repeat steps 3 and 4 until the magnesium oxide is remaining in the beaker. We want to make sure the magnesium oxide is in excess. So magnesium oxide is in excess and all the acid has reacted. We don't want any acid left over. We want to make sure all of the acid has reacted. The reason is because once all the acid has reacted, it's very easy to separate our magnesium oxide. It's not so easy to separate excess acid from the dissolved salt. And then step 6 is filter the mixture. So why do we need to filter the mixture? We want to remove the excess magnesium oxide. So you're going to get rid of that solid and you're just going to be left with the salt and the water, and the final bit will be to evaporate. So there we go. Boom, boom, bam. Right. How should the filtrate be evaporated gently in step 7? Right. Using a Bunsen burner is too harsh. If you heat with a Bunsen burner, you're likely to boil and some of your salt or solution could be lost, could spit out and hit you in the eye. Obviously, you'll be wearing goggles, but it's too violent to heat with a Bunsen burner because the point of the heat is very small, and so it will rapidly heat part and it won't heat evenly. So we can say use an electric heater, or you'll know from biology, you can use a water bath. This is a much better way to get even heat distributed throughout your reactants. Okay, superbulous. I mean, technically, you can use a Bunsen burner if you keep removing the Bunsen burner every 5 seconds. So you're only heating gently, gently, gently. Now we've got a 3 mark amount of substance. 5.6 iron chloride is produced by heating iron in chlorine gas. Here's the equation. 2 iron atoms plus 3 chlorine molecules make 2 molecules of iron chloride. Calculate the volume of chlorine needed to react 14 grams of iron. You should calculate the number of moles of iron. They've broken this down nicely. The number of moles of chlorine that react with 14 grams of iron, the volume of chlorine needed, and they're giving us the relative atomic mass of iron. The volume of 1 mole of gas is 24. So all we've got to do here is start off with which numbers have we been given? Well, we've been told we've got 14 grams of iron and we've been given the AR. So what we want to do straight away, we've got mass and we've got the AR or MR. And I mean, MR and AR are pretty much the same thing. So you've got mass over Mr. Moles. I always use N for Mr. Moles. It's number of moles that. So I'm going to do 14 grams divided by 56, and it's going to tell me how many moles of iron I have. So 14 divided by 56, and that equals, I've got quarter of a mole or 0.25 moles. I use M for my number of moles, and notice I write my units so I know what it is I've worked out. Now I go to what's the next step? Well, we've been asked, so I've done that bit, number of moles of iron. How much chlorine will react with it? Well, look at this. These are called coefficients, and these are the ratio. So it's going to react in a 2 to 3 ratio, which means it's going to increase, right? You're going to go from 2 to 3, and that is timesing by 1.5 or timesing by 3/2. And that is going to give us times 1.5 equals 0.375 moles I now have of chlorine gas. Now we're told that 1 mole is 24 decimeters. Okay, so I've worked that bit out. What's the volume of chlorine needed? Well, if 1 mole is 24, how much is 0.375 moles? That's about a third. So I'm going to need about a third of that. We're looking for about 8 decimeters. All right, it's not 1, is it? It's a lot less than 1. So all we're going to do is go 0.3 0.375 times 24. Sorry, my daughter's going mental next door. She's watching Octonauts. Octo report. Octo report. Yeah, God. Right. Anyway, 9 decimeters. There we go. That's your answer. So super. 3 marks. Boom. Right, let's move on. Oh, Sugar Ray Leonard's. Okay, we're on question 6. Let's go. So this question is about metals. Table 6.1. Table 3 shows information about 4 substances. We've got substance A, B, C, and D. You can see you've got the melting point of each substance, the boiling point. Does it conduct electricity when solid? Does it conduct electricity when liquid? So essentially, A, B, C, and D are either covalent, ionic, or metallic. Giant covalent, giant ionic, giant metallic, and simple covalent. It looks like we've got here. And what they're asking us is which of these substances is a metal? Well, metals have a giant metallic lattice, not ionic, giant metallic lattice. So they're going to have a high melting point and a high boiling point. And so that could be B, C, or D. They've all got high melting points and boiling points. But what do we know about metals? They conduct electricity when solid and when in the liquid state. And there's only one of them here that conducts electricity when solid and in the liquid state. And that is C, which you can see there, conducts electricity when solid because they've got delocalized electrons, carry charge through the metallic lattice. And here we also have it, they conduct electricity in liquid state. So C is our answer. Okay, let's move on. The answer here was C. So we're now going to move on to the next question, which is 6.2. And this says, explain why alloys are harder than pure metals. And this comes down to their structure. So if we look at a pure metal is made up of layers of metal ions. And these ions are held together but can slide over each other. So the pure metals, the layers of atoms can slide over each other. It makes them malleable or ductile. You can pull them out into wires. However, if you make an alloy like steel, you add different sized elements, and that means the layers are disrupted, and so the layers can't slide over each other, and therefore alloys are harder and stronger, but less flexible and malleable. So, what can we say? Pure metals are arranged in layers. The layers can slide over each other. However, if you're dealing with an alloy is a mixture. I should have used the word mixture here, of different elements, and those different elements have different sizes. So, for instance, in one type of steel, you've got iron atoms surrounded with a few carbon atoms in the middle. These different sized elements distort the layers, or you could say disrupt the layers. They change the shape of the layers basically. And this prevents the layers from sliding over each other. The different size elements lock the layers together, and that makes alloys harder and stronger. So better for building bridges and strong things that you don't want to collapse, swords, things like that. Okay, nice one. All right, let's move on to the next part of the question. So we're going to look at 6.3 now. So let's get into 6.3. A student wants to compare the reactivity of an unknown metal Q with that of zinc. Both metals are more reactive than water, than silver. Sorry, my eyes. The student is provided with silver nitrate solution, metal Q powder, zinc powder, a thermometer, and normal laboratory equipment. No other chemicals are available. Describe a method the student could use to compare the reactivity of Q with that of zinc. So they're both more reactive than the zinc in the zinc nitrate solution. Sorry, both more reactive than the silver in the silver nitrate solution, which means they're both going to displace silver. So we're going to see silver form with both. So we could do something where we talk about setting a timer and seeing which one um, shows silver the quickest. But that's qualitative, i.e., you're just using your eyeballs to see, oh, which one, which one did silver form fastest. You could also do something where you weigh the mass of the silver formed over time. But it's better here. They've given us a thermometer. These are exothermic reactions which release heat. So it's better here for us to measure the temperature beforehand of the silver nitrate solution, add the metal, wait till the reaction has taken place, measure the temperature afterwards, and then repeat, and then do the same with the other metal, with the zinc, and see which one gave off the most heat, and that would be the more reactive of the two. And that is more measurable because we're getting numbers, we're getting a quantitative measurement by using a thermometer. So what we're saying here is add metal Q to the silver nitrate solution. It's an exothermic reaction, so we're going to measure the temperature change using a thermometer. Obviously, we want to take the temperature at the start of the reaction before we've added the metal, and then after adding metal Q, measure the temperature every minute until we get to the highest change in temperature. Record that, repeat 3 times, take a mean highest temperature change. So what's the most amount of energy released? We're going to do the mean of that just to make it more reliable. Compare our results, see if we got any anomalies. Um, and now we're going to repeat again the whole process with zinc metal, and then we're going to compare the two temperature changes and see which one is higher. The metal that releases the most energy is more exothermic, is the more reactive metal, is higher in the reactivity series. Now, there are some control variables we need to take into account here, and I've circled the word valid results. You can see that circled. Your method should give valid results. Now, in order to give valid results, we need to keep certain things the same. So you start going down the list, look back up at the top. The student has silver nitrate solution. What do we need to keep the same about the silver nitrate solution? There's two things you need to keep the same in every experiment with solutions, and that is the concentration and the volume. Obviously, if they're what you're changing, if they're the independent variable, you don't keep them the same. But if you're changing something else, and here we're changing the type of metal in the reaction, we're going to keep the concentration and volume of silver nitrate solution the same. Now, what about the powdered metal? what do we need to keep the same? The surface area has been kept the same by using powder. So that's a good thing. They both got the same surface area. However, we need to ensure that we've got the same mass of each. So you need to use a weighing scale and measure the mass of metal Q and of the zinc powder and keep the mass the same. And they're the main things you need to keep the same. You could say keep the starting temperature of the solution the same. We could say use a water bath to heat, etc. But we really got all of the marks here. We've said what we're looking out for, which is the one with the biggest temperature change. We've explained how we're going to carry it out. We've said what we're going to measure. That's the dependent variable, which is the temperature. We've said what we're going to control, which is the volume and concentration of the silver nitrate solution. And we've talked about keeping the mass the same. And there you go. That's all you need to do for this practical to get the 4 marks. It's only a 4 marker, so that'd be lovely. Obviously, you could make it even better if you used insulation and put a lid on. That would reduce heat loss and give you a more accurate temperature change. But that's kind of getting into like a 6-mark question now when we're considering all of those variables as well. Okay, super. Let's move on to the next question. Make sure you like, share, subscribe so I can do more videos and get them to you. And also think about joining my membership, because then you'll have exclusive rights to my membership videos. Okay, question 7. This question is about chemical reactions and electricity. 7.1. Electrolysis and chemical cells both involve chemical reactions and electricity. Explain the difference between the processes in electrolysis and in a chemical cell. Well, the difference is in electrolysis, we're using the electricity or current to split a chemical compound in half. So you might take sodium chloride, molten sodium chloride, you're going to split it into sodium metal and chlorine gas. You're going to break a compound into its components or decompose a compound. Whereas with a chemical cell, you're kind of doing the reverse. You're actually using a chemical compound to make electricity. So rather than using electricity to break a chemical compound, in a chemical cell, you're using chemical reactions to make electricity. Okay, so let's get that down. Electrolysis separates, I can't even spell separates or decomposes a compound, whereas chemical cells, or fuel cells, as we can also call them, chemical cells use chemical compounds or reactions to generate electricity or current. So they're kind of like quite similar, but reversed. Okay, let's move on to 7.2. So if we look here at 7.2, a teacher demonstrates the electrolysis of molten, that means melted, liquid, lead bromide. Bromine is produced at the positive electrode. Complete the half equation for the production of bromine. You should balance the equation. So bromine is in group 7. What do you know about group 7? It's a diatomic molecule. Okay, diatomic molecules, like a lot of non-metals, have a 2 after them because they come in twos. Okay, and there are 7 diatomic molecules. You can think of have no fear of ice cold bread, and that will give you the 7. That mnemonic can give you the 7 the 7 diatomic molecules. So we want to turn bromide ions into bromine, and I'm going to need 2 bromide ions, and that is going to produce 2 electrons and a molecule of bromine. So there we go. That'll get you 2 marks. Okay, let's move on. 7.3. 2 aqueous salt solutions are electrolyzed using inert electrodes. Inert electrodes, by the way, what does the word inert mean? It means unreactive. And your typical substance we use that you have to know off by heart in electrolysis is graphite. Very common question. What's the material used to make the electrodes? Well, it's got to conduct electricity and not react with the substances in the electrolyte. So we tend to use graphite. There are some situations where you use platinum electrodes. but in GCSE we tend to say graphite or carbon. So here it says you have a salt solution, copper nitrate, potassium iodide. What is the product at the positive electrode? What is the product at the negative electrode? Now, we're using salt solutions are electrolyzed. Now, the electrolysis of solutions are different. So there are rules to electrolysis of solutions. And the rules are like this. Rule number one, if a halide is present, that's a group 7 element, by the way. So if you have the ion of a group 7 element present, then that is going to be produced. So if a group 7 element is present, then if a halide is present, then a halogen is discharged at the positive electrode. So at the positive electrode, if a halogen is around, a group 7 element, fluorine, chlorine, bromine, iodine, that's going to come off. If there is no halogen, so if no halogen or halide ion, then oxygen is released as hydroxide ions are discharged. So that's your rule for the positive electrode. And then we have a third rule, and this is for the negative electrode. And there's one rule here. Hydrogen is released, or discharged is a better word, guys. It means goes from a hydrogen ion to hydrogen gas, the element. So hydrogen is released or discharged unless a less reactive metal is present. Now, what metals are less reactive than hydrogen? Generally, it's only going to be copper or silver that you're going to find in practical terms. So copper is the less reactive one. You often won't have silver in electrolysis, but it is possible that silver will come off as it's less reactive than hydrogen if present. So we've got copper nitrate. So the product at the positive electrode, the first thing we do, is there a halogen present? Right, can you see a group 7 element here? Well, nitrate is not a group 7 element. And then that means that we're not going to get like chlorine, bromine, or iodine coming off there because that isn't present. So it means we're going to get oxygen. So we write product at the positive electrode is oxygen. And that's the rule. Now we're going to go to the potassium iodide, and we're going to go, right, what's the product at the positive electrode? These two rules here, 1 and 2, are the rules for the positive electrode, okay? And this is the rule for the negative. So what we do here is we check, is there a group 7 element in the salt? Yes, iodine. Iodine comes from group 7. So if a halide is present, then a halogen is discharged. So we're going to get iodine coming off. Okay, guys? And you could write iodine or you could write I2. Iodine is going to be formed. Okay, let's check the product at the negative electrode. So hydrogen is always released unless a less reactive metal is present. So let's check. Potassium is the metal that's present. Is potassium less reactive than hydrogen? No, potassium is high up in the reactivity series, which means that hydrogen is going to come off. So pretty much hydrogen will always come off when you're dealing with solutions. Okay, solutions are AQ. So if you're dealing with aqueous solutions, then you pretty much always get hydrogen coming off at the negative electrode. The exception is when copper is present in the electrolyte, like there. Okay, cool. Let's move on. Okay. Some students investigated the electrolysis of copper nitrate solution using inert electrodes. Shows the apparatus. We've got positive, negative electrode. We've got copper nitrate solution. We've got a beaker. We've got an ammeter to measure the current. The students investigated how the mass of copper produced at the negative electrode, okay, over here, how the mass of copper produced varied if you left it for a long time or if you changed the current. This is the method used. So what did they do? They weighed the negative electrode beforehand, set up the apparatus, adjust the power supply till it was 0.3 amps, switched off the power supply after 5 minutes, rinsed the electrode with water, allowed it to dry, and then reweighed the negative electrode. Repeated steps 1 to 6 for different times. Repeat steps 1 to 7 at different currents. Okay. Some of the copper produced did not stick to the negative electrode but fell to the bottom of the beaker. Suggest how the students could find the total mass of copper produced. So essentially, if we have our beaker, what they're saying is that the negative electrode, you're going to get your copper atoms. Why are you going to get your copper atoms there? You're going to get your copper because copper is positive. It actually can have a +1 or +2 charge. So most of the time we're going to get copper atoms forming all over this. So if we weigh it again after, it should be heavier. But what this question is saying, some of it didn't stick to the negative electrode and it fell to the bottom of the beaker. And that's going to be in the electrolyte liquid, right? So it's saying, how can we then find out what the total mass of copper was? So what we need to do is obviously we're going to reweigh the electrode, but we also need to get these copper atoms out and include that to the weight of the electrode. So what we're going to want to do is filter the electrolyte using a funnel and filter paper, wash off any electrolyte from copper, then reweigh the copper and add this to the mass of the negative electrode. So, and then obviously to the mass the negative electrode increased. So essentially, you're going to want to find out what your negative electrode was before and then after. If it's gone up by 5 grams, you know you've got 5 grams of copper on the negative electrode. Then you're going to filter this electrolyte solution and weigh the solid residue left behind, which is going to be the copper atoms. Wash it to get rid of any electrolyte stuck to it that's clinging to it. Dry it and then reweigh those copper atoms and add the mass of that to the mass of copper gained at the negative electrode. So I might not have put that clearly in the writing, and that will get you 4 marks. Oh, whoopee-doo, we have a graph. I was wondering when that would happen. The students plotted their results on a graph. Figure 5 shows the graph. We've got 0.6, 0.4, 0.2. This is the mapper of mass of copper produced at different currents. So we've got 0.9, 0.6, 0.3, and we've got times 10, 20, and 30 minutes. And then we have the students correctly concluded the total mass of copper produced is directly proportional to both the time and current. We can see that as the currents increase, we get more copper. And as the time increases for each current, we also get more copper. So both time and current are important. How do the results in figure 5 support the conclusion that the total mass of copper is directly proportional to time? So we can say as time increases, so does the mass of copper. And it is a straight line for each current. So what we're saying by that is that yes, the mass increases, but it's directly proportional. Like at 10 minutes, the mass is there, then 20 minutes, the mass is there. The gradient of these straight lines is the same. So it's going up by the same amount as you increase the time. If it was a curved line, it would not be proportional. Okay, so that gets us a mark. Let's move on. 7.6. How do the results in figure 5 support the conclusion that the total mass of copper produced is directly proportional to the current? Use the data in figure 5 to explain your answer. So this time we haven't got a line to go on, so to speak, in that what we have here is current at 0.3, current at 0.6, current at 0.9. And what I would do here is show that it's directly proportional. So we would take a reading. So we come over here, we'd say that is 1.8. So our reading is 1.8 at 0.3 amps. Okay, so we've got 1.8 grams. If it's directly proportional and I double the current from 0.3 to 0.6, I should double the mass. And what we're going to find is when I draw a straight line, that is going to have doubled. And so if you go to there, that is 3.6. So yes, we double the current, we doubled the mass. So it's directly proportional. Okay. So our answer for this next question would be, as the current doubles from, and I'm going to give the data 0.3 amps to 0.6 amps, the mass also doubles from 1.8 grams to 3.6 grams. And that shows it's directly proportional. Directly proportional doesn't mean that as the current goes up, so does the mass. It means it goes up by the same amount. There's a linear relationship between them. Okay, so if you double one, you double the other. If you triple one, you triple the other. Just like that. Okay, super. We could show that there, like that's 1.8. So if I triple 1.8, 3 times 1.8 is 5.4. And if we come up here, look, 5.4. So if I tripled from 0.3 to 0.9, I would expect a tripling of the mass, and it would go from 1.8 to 5.4. So yes, it is directly proportional. Now we come to this question here, and this says copper nitrate solution is blue. Suggest why the blue color of the copper nitrate solution fades during electrolysis. Well, that's because the concentration of the solution decreases as copper ions, they're the Cu2 plus ions, are removed from the solution. So obviously the copper is coming out of the solution as it forms at the negative electrode. Copper is coming out, and that is meaning that the blue color is disappearing because the concentration of copper nitrate is decreasing. Okay, let's look at this next question. It's worth 3 marks. Determine the number of copper atoms produced when the copper nitrate solution is electrolyzed for 20 minutes at a current of 0.6. We already did that, as in we already found out the mass. So we know it's 3.6 grams. I could go up and look at the graph again, but I showed you that already. So at 0.6, it produced 3.6 grams. Give your answer to 3 significant figures. How many copper atoms are there? Well, the first thing to do is I've got the mass, 3.6 grams, and I've been given the AR. So let's find out the moles. And of course, we can do that by doing mass over Mr. Moles. So I'm going to do mass of 3.6 divided by 63.5. So we're going to whack that in the calculator, 3.6 divided by 63.5, and that is going to give me 0.056 moles. So I have 0.056 moles of copper. And then what we want to do is really 0.57. It's really 0.57. I've just looked at my calculator, but never mind. Now what we need to do is find out how many copper atoms are in that. Well, we've been told there's that many copper atoms in 1 mole of copper. If there were 2 moles of copper, I'd times that by 2. 3 moles of copper, I'd times that by 3. But I have 0.056 moles of copper, or actually 0.057 moles of copper. So I'm going to multiply that by 6.02 times 10 to the 23, and that is going to tell me how many copper atoms there are. So times that by 6.02 times 10 to the 23, and that is going to give me 3.4 times 10 to the 22. That is how many copper atoms there are. Beautiful. Let's just make sure that I got the number 3.6 right. So if we go to 0.6 on there, yeah, it's 3.6 grams. No, not at 20 minutes. It isn't. Oh, you dickhead. All right, guys, excuse my language. I am going to redo this because this is wrong. So this is wrong. And I'm going to show you why I messed up, because it said at 20 minutes. An idiot here did it at 30 minutes. So let's go up to 20 minutes. and it said 0.6. So what I need to do is do a straight line up from 20 to 0.6, draw that straight line over, and that is the mass of copper produced, and that is 2.4 each square. So I'm making 2.4 grams. So I just need to do the same thing, and that is like this, 2.4 grams. So this is going to be the correct answer. I want to find the mass of copper in moles. So I'm going to do 2.4 divided by 63.5, and that is going to give me 0.03779. Now I could round that up to 0.038. So that is my moles, and then I'm going to multiply my answer by 6.02 times 10 to the power of 23, and that is going to give me the number of copper atoms. So times 6.02 times 10 to the 23, and it's going to be 2.27 times 10 to the 23. And I could round that up if I want to 2.228. So if I want, because it actually comes up on here as a 5 as the next number, and because that 5 is bigger, I could round it to 2.28 times 10 to the 22, sorry. Jeez Louise, what's going on? My brain has turned to fudge. And that is your correct answer. 2.28 times 10 to the 22. Sorry about that. I did the wrong calculation. I looked up here trying to save time by not looking at the graph, being a lazy git, and went, oh, it's 3.6, but it actually stated at 20 minutes what is the number of copper atoms. So there we go. All right, let's move on. Oh, said 3 significant figures. Yeah, I did it to 2.28. Okay. We're nearly there, guys, nearly there. I'm dying here. This question is about the reaction between hydrogen sulfide and oxygen. The equation for the reaction is 2H2SG, 3O2G, 2H2OG, 2SO2G. What does H2OG represent? So that is water, and it's water as a gas, so I'm going to call it water vapor. Can spell like that, or if you want, you can spell it like that. All depends how you want. Or we can say steam or water as a gas. So any of those is good enough. So these are all potential answers, got a different spelling, American, English spelling, etc. All the same. Okay, calculate the volume of oxygen required to react with 50 centimeters of hydrogen sulfide. Now, when you're at room temperature and pressure, volume is equivalent to moles. So essentially, Ross, what's going on here? Get rid of that. Stupid Nortons. Don't show again. Sorry, Norton being a pain in my ass. Calculate the volume of oxygen required to react with 50 centimeters of hydrogen sulfide. Well, you can see the ratio is 2 to 3. And what this means is I need to do, the ratio is 2 to 3. So I'm going to go 50 centimeter cubed multiplied by 3 over 2, or 1.5. And that is going to tell me how much I need. So 50 times 1.5. You might say, how can I do that? This is just because the moles of a gas are equivalent to their volume at room temperature and pressure. Okay, so if I wanted to find the moles, I could do 50 divided by 24,000, and that would give me the moles. And then I would just times that by 3 over 2, and then convert that back into centimeters by timesing by 24,000. But I can just do it like this, so it's easier to do it like this. Okay, coolio. No point doing it the long way. Okay, we got 8.3 here, guys, and it says figure 6 shows part of the reaction profile for the reaction. The reaction is exothermic. Complete figure 6. You should complete the profile line, label the activation energy, label the overall activation, label the overall energy change. 3 marks, losing the ability to speak. So you literally are going to get 1 mark for each of this. So complete the profile line. It says this is an exothermic reaction. So you should all know what that means. That means it's going to go down lower. And my products are down here. And in an exothermic reaction, they are lower. If it was endothermic, they would be higher. So that gives me the first mark. Label the activation energy. So the activation energy is actually this, and this is the activation energy. Now I should label that with AE, or I can label it EA, depends who you're talking to, energy of activation or activation energy. The next thing is label the overall energy change. So the change in energy overall, we've got, this is the overall energy change, and then we have all of this energy given out by this reaction. The overall energy change is going to be this little bit here, the kind of net energy change. So energy change, or energy released in reaction. So that's the change in energy there. That is that last one there. Label the overall energy changed. It's this red arrow going down here. Energy released in the reaction there. Overall energy change. Okay, cool. Now we have a bond energy calculation. So 8.4, figure 7 shows the displayed formula equation for the reaction of hydrogen sulfide with oxygen. So we've got hydrogen sulfide plus oxygen goes to 2 water molecules plus 2 sulfur dioxide molecules. We've been given the bond strength of these energies. They've left out one bond. In the reaction, the energy released forming new bonds is 1034, greater than the energy needed to break existing bonds. Calculate the bond energy X for the SO bond. Use table 7 and figure 5. All right, what I'm going to do is just move this down so we've got some space to work. All right, here we go, guys. So a basic equation to know for this is that energy used in bond breaking, so energy in minus the energy out equals the overall energy change. So you kind of got like energy in, it's like energy in bond breaking, take away energy out, which is in bond making, equals overall energy change. Now, we've actually been given the overall energy change. We've been told over here that it is 1034. So what we want to do is set our equation out using X and all these numbers. So first of all, I'm going to say, well, that's 364. Okay, so I've got 364 for each of these black lines, right? S to H is 364. But look, check it out. It's got a big 2 at the front there. What does that mean? That means 2 times. So I've got 2 times 364 times 2. So in a way, I can just write 4 times 364. And that's going to give me 1456. Now I need to put plus, and we're going to add this. Now, each one of these bonds here is worth 498. This double bond, it's quite a big number because it's a double, but it's got a 3. So I need to go plus 3 times 498. So whack in 3 times 498 in your calculator. So 3 times 498, and you're going to get plus 1494. And there we go. We're going to add those together, and that is my energy in, and that is going to secure us possibly 2 marks for our energy in. So plus that to 1456, we get 2950. That's my energy in. I can put the minus sign like I've done over here. And now I need to work out my energy out. Now, let's work out the energy out. So what have I got? I've got HO bond right here. See that HO bond and that. So that's 2 HO bonds, but I've got a times 2. So really it's like 4 times that HO bond. So minus 4 times 464. So let's do 4 times 464, and that equals 1856. And then we've got plus 2 times the X bond. This is the X bond, okay? but I've got two lots of them there and then a coefficient of 2. So it's really plus 4x because there are 4 of those bonds, 2 times those two there. So there's plus 4x. What does that equal? That equals 1034. So now all you've got to do is rearrange this to find x. Let's go and get rid of the 2950. So I'm going to minus 2950 from each side. So minus 1034 minus 2950 equals minus 3984. So what I did is I subtracted 2950 from each side to get rid of the 2950 on that side. So I'm now left with minus 1856 plus 4x equals that. So what I'm going to do now is I'm going to add 1856 to each side, add 1856, and I'm going to end up with, if I add 1856 there, I'm going to get rid of that and I'm going to be left with 4x is equal to minus 2128. And then if I want to find out what 4x is, I simply I'm going to divide both sides by 4. So I'm going to do minus 2128 divided by 4. And I'm going to get minus 532. And so x is minus 532. So the bond energy of S double bond O is 532. So I don't even need that minus, really. There we go. Okay, they'll just ignore it if you put a minus, so don't worry about it. Okay, that'll get you 5 marks. Okay, final question. This question is about acids. Hydrogen chloride and ethanoic acid both dissolve in water. All hydrogen chloride molecules ionize in water. Approximately 1% of ethanoic acid molecules ionize in water. A solution is made by dissolving 1 gram of hydrogen chloride in 1 decimeter of water, which is the correct description of this solution. Let's go and get rid of the 2950. So I'm going to minus 2950 from each side. So minus 1034 minus 2950 equals minus 3984. So what I did is I subtracted 2950 from each side to get rid of the 2950 on that side. So I'm now left with minus 1856 plus 4x equals that. So what I'm going to do now is I'm going to add 1856 to each side, add 1856, and I'm going to end up with, if I add 1856 there, I'm going to get rid of that and I'm going to be left with 4x is equal to minus 2128. And then if I want to find out what 4x is, I simply I'm going to divide both sides by 4. So I'm going to do minus 2128 divided by 4. And I'm going to get minus 532. And so x is minus 532. So the bond energy of S double bond O is 532. So I don't even need that minus, really. There we go. Okay, they'll just ignore it if you put a minus, so don't worry about it. Okay, that'll get you 5 marks. Okay, final question. This question is about acids. Hydrogen chloride and ethanoic acid both dissolve in water. All hydrogen chloride molecules ionize in water. Approximately 1% of ethanoic acid molecules ionize in water. A solution is made by dissolving 1 gram of hydrogen chloride in 1 decimeter of water, which is the correct description of this solution. Well, 1 gram isn't a lot of mass, so it's only a tiny bit. So you're going to make a dilute solution because it's 1 gram in a decimeter. A decimeter is a liter. So it's going to be dilute. And hydrochloric acid or hydrogen chloride, which is a gas, if you dissolve it in water, it forms hydrochloric acid, HCl. And that is a strong acid. It fully dissociates from HCl into hydrogen ions and chloride ions. So the answer is going to be a dilute solution of a strong. Yep, a dilute solution of a strong acid. Oopsie, I've ticked concentrated solution. Well, it wouldn't be concentrated because it's only 1 gram, so I need to tick the 1/3 down because it's only 1 gram in a litre. So there's not a lot of it, but what it is strong. 9.2, which solution would have the lowest pH? Think about what this word means. Lowest pH is like, say, which one is going to be close to like pH 1, 2, or 3? Now, you should remember that low pHs are normally possessed by strong acids. You can have a weak acid with a low pH, but we've got the options of some strong or weak acids. Ethanoic acid is a weak acid, so I'm going to get rid of those two. Although it's the potential, if you have a very high concentration, you can have a low pH of ethanoic acid. So here we're looking at hydrogen chloride solution. Of course, this is a strong acid, and what that means is it fully dissociates or fully ionizes when in solution or when dissolved in water. And so which one is likely to have the highest concentration? That's going to be the 1 mole per decimeter hydrogen chloride solution. So that is likely to have the lowest pH here. We've got a little method here to look at. A student investigated the concentration of a solution of sodium hydroxide by titration with a 0.0480 mole per decimeter ethanoic acid solution. I sense a titration, peeps. Measure 25 centimeters of sodium hydroxide into a conical flask using a 25 centimeter cube pipette. Add 2 drops of indicator to the sodium hydroxide solution. Okay, fill a burette with 0.0480 ethanoic acid solution to the 0 mark. Add the ethanoic acid solution to the sodium hydroxide solution until the indicator changes color. Read the burette to find the volume of the ethanoic acid solution used. Suggest 2 improvements to the method that would increase the accuracy of the result. Add 2 drops of indicator to the sodium hydroxide solution. That's fine. Add the ethanoic acid solution to the sodium hydroxide until the indicator changes color. You need to swirl, swirl the conical flask after each time adding acid. So that is going to ensure that the reactants react fully. And then it says until the indicator changes color, make sure the color change is permanent. So you need to make sure that the color change is permanent because sometimes it changes color and then it goes back to the previous color. So you've got to keep swirling it and wait for 10 seconds or so to make sure that that color change is permanent. Also, to make it more valid, we should repeat and find a mean titra. So that means ones that are within 0.1 or 0.2 of each other. Do the repeats and calculate a mean only using concordant results. Another thing we could do is use a white tile to make observing color change easier. So any of those are good. Lovely jubbly. Right, let's move on. Calculation incoming, I suggest. Ethanoic acid is a solid at room temperature. Calculate the mass of ethanoic acid needed to make 250 centimeter cubed of a solution of concentration 0.0480 mole per decimeter. And we've been given the MR. So immediately we're like, oh my God, what do I do? Well, the moment you get given this in chemistry, you know you're probably going to be using mass over MR times moles. And if you're given this 250 centimeter cube and a concentration, you're probably going to be using this concentration one, which is N over CV. So calculate the mass of ethanoic acid needed to make 250 centimeters. So that's a volume of and a concentration. So the one I've got 2 of, I've got 2 of these, okay? If I try to use this equation, I've only got MR at the moment. I don't have the mass and I don't have the moles. So I need to start over here with C and V, and I need to do the concentration, which is 0.0480, and I need to multiply that by V to get N. Now, you must remember you got to divide by 1,000 to put into decimeters. So the concentration is in decimeters. I need to turn the volume into decimeters. So I need to do times 250 divided by 1,000, which is essentially 0.25. And that is going to give me my moles. So let's whack that in the calculator right now. And that is 0.0480 times 0.25. And that is going to give us 0.012 moles. And that means I can take the N over here, times it by the MR, so times moles by 90, and that is going to give me the mass, because that's my MR. So times that by 90, and that's going to give me my mass, which is 1.08 grams. And you should know mass is always measured in grams. So you should know these two calculations off by heart. If you don't, you're not going to get a level 9 in GCSE chemistry. So make sure you learn those chemistry calculations. They will not give them to you in a higher paper. All right, 3 marks. The student found that 25 centimeter cubed of the sodium hydroxide solution was neutralized by 15 centimeters of 0.0480 mole per decimeter ethane acid solution. The equation for the reaction is ethane acid plus 2 moles of sodium hydroxide makes this salt here, sodium ethane plus water. Calculate the concentration of sodium hydroxide solution in moles per dm. So this one is nice. We just have to use this one equation, which is the titrations equation, N over C times V. And you're just going to use coefficients. So like you need to use that as well to get full marks. Now we're going to have been given 2 of these things. So you've got to hunt that down. Student found 25 centimeters of sodium hydroxide was neutralized by, look, I've got 2 volumes, but 2 of them are for ethane acid. So I want to start there. So I've got volume 1 and concentration 1 of ethane acid. I can't work anything out about the sodium hydroxide at the moment because I've only got the volume of sodium hydroxide. I don't have its moles or concentration. So, and that makes sense because we're going to calculate the concentration of sodium hydroxide solution. So first thing that you can work out is N for the ethane acid. So let's work that out. Remember what I said with the volume, we're going to divide it by 1,000. And then we're going to multiply that by the concentration so that we can get the moles. And once we have the moles of ethane by doing 15 divided by 1,000, and that is 0.015, we're timesing that by 0.0480, and that is going to give us 7.2 times 10 to the minus 4. So that's 0.00072. And that is the moles of ethane. Now, what is the relationship, the coefficient here? It has a 1 to 2 relationship. So for every mole of acid, I need 2 moles of alkali. So I'm going to double that by timesing by 2. And I'm going to get 1.44 times 10 to the minus 3 moles of sodium hydroxide solution. Great. So now all I've got to do is, this should really be 4 marks, but I've just worked out the moles of sodium hydroxide. And of course, the question wanted concentration. So we're going to do N over V, and we know that V was 25. So we're going to go 1.44. But we don't want to divide it by 25. Let's not make that mistake. It's titration. Always divide your centimeters by 1,000. So we're going to divide that by 25 over 1,000. And that is going to give us our concentration. So we're going to have a concentration of 0.0576. Okay, guys, I hope you found that useful. Make sure you share, like, subscribe. Let's get to the marks. Smash those exams. Good luck.
You're still here? It's over.